logarithmic response of cones and rods. The response of the cones and rods to light is non-linear. In fact, many image processing systems assume that the eye's response is logarithmic instead of linear with respect to intensity. To test the hypothesis that the response of the cones and rods are logarithmic, we examine the following two cases. If the intensity response of the receptors to intensity is linear, if the intensity response of the receptor to intensity is linear, then the derivative of response with respect to intensity should be constant. This is not the case as seen in the next figure. To show that response to intensity is logarithmic, we take the logarithmic of the intensity response and take the derivative with respect to intensity. This derivative is nearly a constant, proving that intensity response of cones and rods can be modeled as a logarithmic response. Another way to see this following, note that differential of the logarithm intensity, differential of the logarithm of intensity, I for intensity, differential, T for differential logarithm of intensity equal to di by di divided by I. Figure 2.31 3 bar 1 shows the plot of di for the intensity response of the human visual system. Since the plot is nearly constant in the middle frequencies, we again conclude that intensity response of cones and rods can be modeled as a logarithmic response. Magnitude of sensitivity experience in y-axis, this is actually magnitude in this figure, magnitude of sensory experience according to the Weber-Kruger law, and the figure A shows the actually measured sensitivity of the eye to difference. That is, the magnitude of sensory experience he is responsible. He is represented along the ordinate as the function k in x-axis intensity illumination. Scale is 10 to power minus 3, 10 to power minus 1, 10 to power 1, 10 to power 3, 10 to power 5, 1x, 10 to power 7. Here 10, 20, 30, 40, 50. The magnitude of sensory experience, is represented along the ordinated as the function k in Rn here. This one here. For the amplitude of the eye according to the graph, the eye can distinguish 50 equally spaced levels sensory experience of the roughly 3.5 lie in the linear region. B, the figure B, magnitude maximum contrast K, intensity illumination. Here some linear, here bell-shaped curve, here up to linear, then constant. Which one is constant? Approximately this one, maximized K. here linear, then here also linear, you can say negative linear. This graph shows the actual sensitivity of the eye. Actual sensitivity of the eye difference as measured by experiment. If the Weber-Wegner law were to hold exactly rising straight line in A, rising straight line in A, this curve taken from rank 1.1 would be parallel to the x-axis. Here, this is parallel to the x-axis. After that, approximately going same like that, then like this. This is also at 10.5, but 10.5 here reduced. Simulation, simultaneous test. Simultaneous contrast. Simultaneous contrast phenomenon is illustrated below. The small square in each image are the same intensity. Here all are same intensity. Because the different background intensities, the small squares do not appear equally bright. Perceiving the two squares are on different backgrounds as different, even though they are fact identical, is called simultaneous contrast effect. Psychologically, physically, we say this effect is caused by the difference in the backgrounds. But what is the psychological mechanism behind this effect? Lateral inhibition record signal from nerve fiber receptor A. Illumination of receptor A alone causes a large response. Add illumination to 3 nearby receptors at B cause the response at A to decrease. Increasing the illumination of B further decreases A response. Decreases A's response. Thus, illumination of the neighboring receptors inhibited the firing of receptor A. The inhibition is called lateral inhibition because it is transmitted laterally across the retina in a structure called lateral plexus. A neural signal is assumed to be generated by a weighted contribution of many spatially adjacent rods and cones. Some receptors exert an inhibitory influence on the neural response. The weighting values are in effect the impulse response of the human visual system beyond the retina. Here logarithmic receptors, weighting factors, these lateral inhibitions, neural signals. Number. Match band effect. Another effect that can be explained by the lateral inhibition. The match band effect is illustrated in the figure below. The intensity is uniform over the width of each bar. However, the visual appearance is that each strip is darker at its right side than its left. Here darker, that right side. Intensity uniform over the width of the each bar. Step chart photo. Match band. Step chart intensity distribution. Step chart. match band. The match band effect is illustrated in the figure below. A brighter bar appears at position B and a dark bar appears at D. Dark, bright bar here, appear bar. Here, dark bar. D. This is the D. Modulation transfer function, MTF experiment. Modulation transfer function. An observer is shown two sine wave grating transparencies, a reference of grating of constant contrast and the spatial frequency, and a variable contrast test grating whose spatial frequency is set at some value different from that of the reference. Contrast is defined as the ratio maximum minimum divided by maximum plus minimum. In numerator, maxima minus minima divided by in the denominator maxima plus minima. Where maxima and minima are the maxima and minimum of the grating intensity respectively. The contrast of the testing grating is varied until the brightness of the bright and dark regions of the two transparencies appear identical. In this manner, it is possible to develop a plot of the MTF of the human visual system. Note that the response is merely for an exponential sine wave grating. Note that the response is merely linear exponential sine wave grating. Linear, sometimes linear. Here also linear. Monochrome vision model. The logarithmic linear system I model provides a reasonable prediction of visual response for wide range of intensities, that is intensities. However, at the high spatial frequencies, this is 0.18 up to 60 spatial frequency cycles per degree, relative sensitivity 0.4 to 10. However, high spatial frequencies and at very low or very high intensities, observed responses differ from responses predicted by the model. MTF measurement with the experimental sine wave grating. This figure. So light exhibits some properties. Light exhibits some properties that make it appear to consist of particles. Other times behaves like wave. Times behave like wave. Light is electromagnetic energy. Light is electromagnetic energy that radiates from a source of energy or a source of light or a source of light in the form of waves. Visible light is in the 400 nanometer to 700 nanometer. Okay. 400 up to here only visible. 400, 500, 600, 700.